First of all, I beg your pardon because I am used to call Harish as Harish and not Mr. Harish, because he used to be one of our FOSSEE interns. We had worked together as team members. Harish used to be our employee at FOSSEE IT Bombay. And now we are actually very much overwhelmed that he's doing so much good in his career. And today he's one of the esteemed advisory board members of FOSSEE. It's really very much overwhelming to witness such a growth. So congratulations, Harish.
Thank you, ma'am. Thank you very much.
Yeah, and let me introduce him to you all. So Mr. Harish Jairaj is the founder of Codynamics. He's a CFD engineer with expertise in ANSYS Fluent, OpenFOAM, and numerical modeling. His work focuses on utilizing commercial tools and customizing open source solvers for industrial and research applications, particularly in multi-phase flows, HVAC, and external aerodynamics. Alongside his engineering practice, he is a Python developer specializing in desktop software development for scientific computing, building tools, and enhancing simulation flows. Mr. Harish also contributes to the CFD community through Codynamics, an initiative dedicated to creating structured learning resources, tutorials, and practical content that make OpenFOAM and applied CFD more approachable. Through platforms like Udemy and YouTube, Codynamics has helped learners worldwide to strengthen their skills in CAD, CFD, and scientific computing. With a long-term vision of advanced CFD technologies, Mr. Harish is committed to developing innovative solutions and creating platforms that bring in high-end simulation tools closer to engineers, researchers, and industries. So, yeah, here is he in front of you. So very soon he'll be presenting his session today. And we are really thankful to you, Harish, for joining the session.
Thanks for the introduction, ma'am. Yeah, very glad to be back here.
Yes, we are also very glad. So over to you. You can start the session.
Okay, ma'am. So I'm Harish Jairaj. I represent my small startup, Codynamics. So here I'm just going to give a small talk on potential use of CFD for enhancing HVAC designs and application. This is not going to be very technical. I'm just going to try to give a spark in the participants to try out HVAC CFD in general. Because when I started with CFD, most of the people and most of the tutorials online were focused on aerospace and mostly mechanical. So when I mean mechanical, it's mostly automotive, aerodynamics and such kind of simulation. But when I moved to industry, I realized that there is huge scope for HVAC, especially in a country like India, where we are trying to build a lot of buildings. HVAC designs is very much necessary, and there is a huge scope for CFD here. And apart from aerospace, I just want a lot of people to try out HVAC, and if it interests them, I just want them to pursue in that direction as well. So my talk is mostly going to be exploring a lot of domains within HVAC, and people might not even know that these are actually part of HVAC. I mean, what is HVAC? HVAC is heat, ventilation, and air conditioning. But it's not just restricted to that. There are many applications that is bringing in design optimizations and so on. But many people who are learning CFD or exploring CFD might not know. So I hope it makes a change after my presentation. So the overview is going to be why simulate HVAC with CFD first of all. So if you take a CFD case in general, we do it because experimentation is expensive. So when I mean experimentation, if you want to build an aircraft or a car and do the aerodynamic analysis in a wind tunnel, then it's going to be very expensive. So we brought a numerical method where we can do the CFD and iterate on our designs, and we consolidate the designs. Let's say we have 50 designs, we consolidate to 5 to 10, and then we manufacture and test only those, because numerical simulations are going to have errors. But think about a building. At least a aircraft or car, you can manufacture 5 different things, and then eventually you can choose one and put it for mass manufacturing. But what about the building? You can construct it only once. So CFD becomes very necessary to avoid a lot of hassles in constructing, demolishing, or saving a lot of cost. So it is very essential to do it very accurately and provide a valuable resource to the architects and the engineers, the civil engineers, to make the overall building comfortable to live in or work in. So we will just look at many applications where HVAC simulations are coming in. So as I mentioned, HVAC is heat, ventilation, and air conditioning, but there is another component called refrigeration, HVAC and R, but usually it's known as HVAC or HVAC. So I'm just going to keep it that way. We are not going to look at refrigeration. And just to start with, as you might already know, you have seen, I think, 2 days of lectures. You have seen a lot of domains apart from aerospace as well, like hydraulics and everything. Very differently, this kind of simulation is going to give a different perspective. Like, we are not going to just see data out of our simulation, but visualization matters more than the data here. Of course, the data like temperature drop, the pressure drop, the contaminants are going to be necessary, but visualization plays a huge role in HVAC. I'll try to explain why it is in that way as we look through the slides. So you know what is CFD by now, and the key goals in any HVAC simulation is to ensure thermal comfort and indoor air quality. So when I talk about buildings, buildings are not going to be aerodynamic in a lot of senses, as you might know. So what do we actually look at the simulation? So we want to ensure the thermal comfort, because when you are going to live in, you want to feel comfortable, and indoor air quality. As we move towards the climate change and the pollution, we are more focusing on indoor air quality now. And we also have to improve energy efficiency. Just because we want to keep more air quality, we cannot keep running air conditioners all the time, because the energy is going to be overheating, and that's going to be expensive, and it's eventually going to cause more damage to the earth. And we also have to optimize airflow distribution and ventilation, because even though you have fans, natural ventilation plays a lot of role to give you proper comfort. And we also have to evaluate alternative HVAC designs before deployment. As I said, constructing and feeling bad is not a choice here. So we have to make sure everything is perfect, and then we have to start the construction. So major types of CFD simulation in HVAC is very broad, but if we have to classify, we can basically put it to 5 different groups. So we can see the first type would be airflow and ventilation simulation. This is the most common type of ventilation simulation that we would be doing with any type of HVAC simulation. So the objective would be to model the airflow behavior, and we will be looking at the velocity distribution, recirculation zone, and optimize diffuser vents and duct placement. So these are not something that we would look in a daily basis in a construction or a house. If you look around, you will not be able to see this a lot, because we are not focused on that. But if you take a data center, office, high-rise buildings, then they are very much cared about the velocity distribution, because you should not feel very uncomfortable when you enter a room. If the air is just blasting through the ceiling fans, you're not going to feel very comfortable. And if you take a data center, then the heat generation is massive, and you have to properly vent it out. And if you are in a high-rise building, then you are going to have something called a AHU, air handling unit, which is mostly kept underground, and it's the basic chiller unit. It's like centralized. Uh, all the HVAC components are going to cool your air and then push it through the entire building. And during this process, the pumps are going to heat up, the temperature is going to rise in the air. And this is a whole lot of problem, because whatever temperature you are bringing into the air, it's not going to be supplied eventually. So this whole problem can be solved only with simulation, because if you try to experiment, it's going to be expensive. And the second type is the thermal comfort analysis. This is where we are getting close to our daily, whatever we are seeing in our office or houses. So if you take the thermal gradients or predictive mean vote, it's a mean vote is might be a new term. It's like if you put 100 people in a room and you set a temperature, and if you get a vote from the people, like how comfortable are you feeling on a scale of -5 to 5 or -10 to 10, depending on the study, then what is the rating that you are giving? So this is like a comfort analysis, and the opposite is the PPD, which is the predicted percentage dissatisfied. So we have to take these data, and then we have to simulate in order to see how comfortable someone might feel on an average inside a room. So this is mostly useful in office rooms, passenger cabins, and classrooms. And if it's a big university and you're building a big classroom, then this is very much necessary, because if you think of a huge room, the air vents are going to be close to the walls, and students sitting there might feel very uncomfortable, while someone sitting in the middle is going to feel very hot. So you have to properly look at the recirculations and how far your airflow can move, or should you place some inlet at the middle of the room in order to keep the temperature uniform. So now we are getting closer to what we would see in a daily. But even further, if you look at the indoor air quality, that's the third type of simulation, we are bound to see it everywhere. So if you take hospitals or clean rooms, laboratories, or as an engineer, if you are working in a manufacturing facilities, then these kind of or even hotels or restaurants, we can see this kind of simulation coming in if it's a big hotel. So this models the simulation of CO2 dispersion. So if you are in a confined room, like a hospital, you don't want external air to be coming in very regularly. But even with an air conditioner, your carbon dioxide buildup could be slowly creeping on you, and it can cause problems. And if you are in a restaurant where there is, maybe they are storing alcohols or some kind of spirits while cooking, so that's VOC, which is volatile organic compounds, then these kind of volatile liquids can evaporate in room temperature or pressure, and it can disperse, but you don't want that to happen. So how do you contain that very locally without a refrigerator, even if you store in normal condition? And these kind of simulation come in IAQ, which is indoor air quality. And then there is the energy performance simulation, where we couple simulation to heat loss or gains. So let's say you have a big factory and there is a generator running. You want to push the DG air somewhere where it will not affect the factory itself. If you're pushing it very close to the factory, it's again going to heat up the indoor air and it's going to be bad. And the other part, because it is heating very regularly, you're not going to get the maximum efficiency out of the HVAC machine. Let's say you have a data center and your chiller is not working fine, then it is a problem. But what if the chiller is working fine, but the heat of the chiller is actually affecting your entire room temperature? Because chillers are usually kept on the roof. So this is again a big problem. So how high do you want to keep the chillers from the roof so that you don't get bad effects from it? And this is energy performance simulation, but it's not confined to this alone. Let's say you want to build a room and you want to keep ACs. How many ACs do you keep to optimize the airflow? That's the first part. But as you increase the air conditioner, you're going to get more comfort, but you're going to lose more energy. Like you're going to consume more energy, which is again bad economically and globally. So you have to also optimize that in a sense, so that you get a trade-off between the energy consumption and your comfort. So you cannot just prioritize either of them. So it has to be a trade-off between both. And comes the last one, which is the system performance. It's mostly not related to CFD, but since it's type of HVAC simulation, we are putting it here. This is more like a circuiting, let's say a MATLAB kind of simulation, where you have a whole lot of system. In a manufacturing facility, if you see, they are not going to get the usual voltage or wattage with regular frequency. They are going to get higher, and some components might need higher voltage, some components might need less. So you must have electrical regulators so that sudden voltage hikes are not there for certain components, or else our compressors, impellers can fail eventually, which is not a good thing in a confined scenario, right? Because most of the HVAC components are going to be within a confined room or inside the walls. It will affect the whole manufacturing facility. So these kind of simulations also exist apart from CFD, but just wanted to cover it. Now, HVAC isn't limited to air conditioning ducts as we might think. It's wherever there is air, temperature, and comfort. So let's take a very small example. You're hopping onto a car and you feel comfortable when you turn on the AC more than when you just have your windows open. It is because we know how the air vents distribute the flow to the passengers, how the defogging works when you are in a different temperature condition. If you have a heater on in your car and there is rain outside, you're going to get fogging. So how do you defog the windshield and what is the optimum temperature? So these are not for the regular users, but for the manufacturers or the designs, the automotive designs. Those teams are going to look at this kind of simulation, and this is very huge in India. And all the manufacturers are looking through this, especially for the windshields and the headlights, because fogging on headlights is not a good thing. And then there is also a small part of how the sunlight affects the cabin temperature, because although we can put tint sheets on the windows, there is a government regulation on how black can your windows be. So again, it's a trade-off. So we have to see how much of light can it pass through, what should be thickness of the glasses. So there are radiation and there is light directly affecting. So we should also have a trade-off between the light and the radiation. So this is very small. And if you just go slightly wider, you can see trains and aircrafts doing similar kind of simulation. At least in trains, when the doors open in a metro or something, we can get fresh air, but it also takes in pathogens and pollutants inside. So we want to avoid such kind of scenario, and we bring in air curtains there. So if you enter some hotels or shops, you might have seen they would have had air curtains in the entrance. So such kind of air curtains are usually kept in the entrance of aircrafts or trains in order to avoid external pollutants coming in, because it gets very hard to remove. And then, as we already saw, we have data centers where we have the hot aisle, cold aisle, where we don't have a lot of forced convection. Instead, we have to take the thermogradients and look how we can provide the vents in such a way it naturally convects in order to reduce the energy consumption by the HVAC components. And we should also ensure server reliability, because as you might know, data centers are semiconductors, and when they heat up, they don't perform very well. It can crash. So we have to keep the temperature in a controlled range, and air conditioners alone are not going to be very helpful in a data center. There is a whole lot of simulation like chilling, and there is vent simulations, there is forced convection sometimes. And coming to the last part, which is the office or classroom spaces, that's even bigger, and we have to ensure balanced air distribution, because if there is CO2 buildup, it's not good. If it is also heat buildup, it's again not good. It's not going to be energy efficient in comfort zones, especially if it's an office, right? So here I have two images showing two extremes of the simulation. One is extremely large indoor simulation, like a stadium where it is open, but you should definitely provide air conditioning so that the people don't feel it very hot. Anyways, the air is going to get hotter because it's open stadium. Still, you have to provide the air conditioning. So what should be the temperature in order to make them feel comfortable even when the temperature is not contained? The other extreme is the external airflow around a city, where if you are constructing a building or if you are taking an office at some floor in your in a big building, then how do you optimize the airflow? Because we will get the data from the observatory or satellite data on how the wind changes throughout the year. So you can optimize in such a way that you can make use of natural ventilation to some extent, but there is also wind movement, so that when you open your windows, it should not blast your windows, right? There are other components as well, but I'll just keep it to very basic, which is the external flow, where you are trying to optimize your construction or office placement windows based on natural airflow. And again, as I said, the door curtain systems, this is very important in a lot of places. And as a manufacturer, they will do the simulation, not as a client, but because it becomes a standard in a way. So once you manufacture for certain size, it's going to stay the same. But there are a lot of energy efficiency optimization to be done here, because it has a rotor part. It wears out soon, and there is also a motor. So you have to optimize the energy in such a way, or optimize the design in such a way you get maximum airflow even for low RPM or low energy consumption. And the other extreme is CO2 spread. Let's say through the air curtain somehow people enter, and then there is CO2 spread inside the hall, like a concert hall, because there is no vent outside. These are mostly acoustic optimized buildings or hall, where there is less number of vents so that the sound doesn't go out, or it's contained. It's designed for acoustics. So we have to place the air conditioning system in such a way it's not producing a lot of noise, and also it is venting carbon dioxide properly. It should not affect the overall acoustics as well. So this becomes acoustics plus CFD problem. And this is regular office kind of simulation. If you have two options for air conditioner placement, where do you place, left or right, which gives you maximum placement? And if you take architecture inside this, people might want to place plants inside. when we think about CFD, we are not just looking at the thermal, but also we have to look at the aesthetics there, because some people might prefer keeping indoor plants, which is not good with fast moving air, right? So we have to place the plants in a recirculation region where the pressure is not so high and also the air movement is not so high. So it is mostly close to the air conditioner, and this kind of simulation is also there. And these are mostly our architects will be the customers for this kind of simulation. And then there is a fan optimization design. This is coming to design optimization. This can be merger of both aerospace as well as not aerospace, but mostly aero related simulation plus HVAC, because you have to look at the airflow as well as the design optimization for maximum airflow. So where do you place the fans? That's one kind of simulation, and how big your fan should be, or how optimized, or how much RPM is your fan is supposed to run to provide maximum airflow in a room that's not rectangular. If it's rectangular, we can easily say put it in the middle. But if it's not a rectangular room, if it's arbitrary, then how do you place your fan? These kind of simulations come in. And this is very good in OpenFOAM, because OpenFOAM has the sliding mesh motion simulations, like Pimple Foam offers that, and we can use these kind of simulation to do that. And I have done several simulations for this kind of application. It is really good. So if this is also an interesting field, because when you are doing a dynamic mesh motion simulation, you get both uh, the both the scopes, like HVAC as well as aerospace, because if you're also working on propellers, it's going to come in handy. And talking about other different kind of scenarios where you will do HVAC, there is high rise and urban microclimate studies, where your building is in scenario where the climate changes very fast, and how does your wind interact with the building? If you want to open your windows, it should not feel unpleasant, or it should not draw in a lot of dust. So your geographical placement is also very important, and LDS kind of simulation come in play here. And this also aids in natural ventilation. And if you are in a court, like a golf court or something, in those cases there will be a small area where people will be standing. And how do you place your golf area and your building in such a way the air is not affecting the seating placement, right? So this is a kind of simulation which is not very popular in India, but it is there, so you have to know. And there is natural ventilation in buildings, and there is wind driven cross ventilation. When you think about ventilation, we might think ceiling fans, air conditioners, but in countries like Germany, people prefer natural ventilation more than the air conditioner, at least for residential areas or very small offices, because there is a natural airflow. And how do we make use of that to our benefit to the maximum? And there is stack effect. So stack effect is like there is cold air in the bottom because of the heaviness of the air, and it slowly heats up. And if you're on a top part of a building, then it's slowly going to rise. And when you have your windows open, you're going to get hot air through your windows. It's very minimal, but it has an effect that is happening. And there is atrium, like if you have a balcony, how do you place your balcony, and do you really need a ventilation system in the balcony, or is your natural airflow enough? So these are luxury building kind of thing, but still it's necessary. And there is underground station. So this is very popular in Indian scenario, because we have a lot of subways, metros in those cases, and a lot of parkings in buildings. So smoke movement becomes very necessary. If there is unfortunately a fire, how fast can your fire be extinguished, and how fast can the smoke move? So fire extinguishers are there everywhere, but how fast can the smoke move? Because smoke is toxic. Even for the firefighters, it's going to be toxic. So how fast can you move it, and how do you place the ventilation system? How do you contain the fire? So there is a whole domain called FDS, fire dynamic simulation. So you can look that as well. And this is a very interesting domain, because if you are also from chemical background, you can see how do you extinguish using certain chemical and chemical reaction. This also comes under HVAC. And then again, the general large public spaces like auditoriums or stadiums, especially in malls, because the overall energy optimization is also important. Overall placement, like the design of the building itself, is very necessary. So as a CFD engineer, you'll be giving inputs to the architect or the civil engineer on whether this placement of air conditioner is good or not, whether it's going to provide maximum airflow throughout the building in a uniform setting or not. And this is a data center simulation image. So as you can see on the left, we have 4 racks and 2 plus 2. We can say it as 2 plus 2. Each rack is going to have a lot of servers, and these servers produce massive heat. So around 95 to 100 degrees Celsius of heat per processor. So we have two things. One is called the cold aisle, and there is the hot aisle. And the hot aisle is between those two racks. So these hot aisles come in, and because it's hot, it moves up. And the other side, we have the cold aisle where we place the air conditioners or pass in the chilled air. So because of the pressure gradients, it's going to take in the cold air, cool it slightly, and then the hot air moves up. After it moves up, we have to provide proper ventilation system or exhaust system so that the heat goes out evenly or properly. So even if it is very abrupt, we will not get proper airflow. It has to be very slow, and there is a thing called residence time. So even if your air is moving very fast, you're not going to transport a lot of heat, and it's just a lot of energy consumed in transportation of heat or the air. So we have to see whether the residence time is proper so that the convection takes some time, the air takes in proper amount of heat, the maximum amount of heat, and then it goes out so that the processor cools efficiently. So this is another kind of situation where we have to look at data and not just visualization. And if you take on the right side, we are looking at the streamlines. So on the hot aisle, we are looking at the streamlines and see how close should those racks be placed in order to avoid the flux from one rack to the other, because the heat of one rack should not go on and heat the other rack. So what should be the distance? Now it's again visual based more than just data based. So we have to look how many number of racks can we safely place inside a room. So this is another kind of visualization based simulation. And if you look at a 3D scenario, we have whole lot of data centers, and we have different placements, and how do you put the vents, where do you place the door of the data hall, and how do you prevent the heat from going into the outside through the door, because there might be an office, we don't want the heat to exhaust there. Then how do you place an air curtain? So it becomes a whole lot of combination of simulations that I have told till now. And if you look at the other parts, let's say we looked at the broader picture like data centers and big halls. And if you look at a very small space, like a office space, then we have to also see how this sunshine comes in. There is a lighting, because always we cannot place extra lighting. Sometimes people prefer natural lighting. And how many windows can you place in a wall? How much is it going to affect? Because radiation also comes in. Sun is going to heat up your room. And how much is your air conditioning going to work despite the heating from the AC? Sorry, heating from the sun. So these kind of simulation is gaining traction right now, because people are getting conscious about getting enough sunlight, and they want it even inside the room, but it should not affect the overall comfort inside the room. So we place both air conditioner and also translucent windows where we will get enough light from the sun. And this is a whole lot of different simulation, and it is going to be modeling internal temperatures. And then we have the radiative exchange between surfaces. Let's say you have two buildings very close, and one is having the outdoor unit of air conditioner here, and the other building has a window there. So this heat is going to affect it, not so much, but it's going to affect it anyways. You cannot open the windows. Then in those scenario, how do you actually place a sunshade, or how do you prevent the air from coming inside? How do you place the windows in such a way? So even if the building is already there, it's not like doing the simulation before the construction. Even if the windows are there already, how do you prevent? So you can keep an air conditioner or window AC near that, so you can prevent something. So this is very subjective, but it depends on the simulation, the scenario, and what kind of result are the customers expecting. But eventually, if you take the radiation apart from the heat from the motors and everything, it's going to affect, and we have to prevent it. And if you take a building envelope design, we have to analyze the insulation. If you take a roof, nowadays people put weather cores on the roof so that the heat doesn't enter. But one step ahead, we can place solar panels on the roof, so we also get electricity and also avoid heat from entering through the roof. Because if you are on the top floor of a building, and if you try to put a ceiling fan, and if there is no weathering cores, you are essentially pulling the heat from the ceiling and you're pushing it onto the room. This is really bad even if the people inside the room want a proper air circulation, apart from air conditioner, you are going to get like a more hot air than the cold air because you're on a top floor. And how do you optimize that? How much weathering course do you want to put? How much radiation do you want to reflect? So these kind of simulation is coming under the building envelope design. And we should also be looking at the glass buildings. If you are in a glass building, the radiation is going to affect a lot. So if you take some buildings in Chennai, you can see that there will be glass on the outside and there is a confined wall on the inside. The glass is just for decoration, because if you just keep glass windows, it's going to heat up further and it's not a good thing. So there is this kind of simulation where aesthetic comes into play more than just comfort. And there is also seasonal or diurnal studies where the seasons affect how your windows placed. Because let's say in one season you are getting maximum airflow during the winter, so you want to prevent it because you don't want a very cold air. But in the summer you're going to get it very hot. So how do you manage? Do you place two windows, use it alternatively? This is not in a common household scenario, but when it comes to an office or high-rise buildings, this is going to matter a lot. So it's like this kind of scenario where there is a roof and it heats up due to radiation, and it should not affect how the building heats up. And finally, coming to the air quality and health oriented scenarios, where again now it is gaining a lot of traction. So after COVID, because in COVID we were advised not to use air conditioners. As I was saying already, air conditioners help in removing those pathogens. So why did we not use air conditioners, right? Because the air conditioner, before removing the pathogens, it creates a recirculation inside the room to collect everything and then push it out. But in a scenario like COVID-19, if one person is affected and if they disperse some pathogens onto the air, then the recirculation is actually going to make things worse and not better. So we have to be very careful in such kind of scenario, and not just in a scenario like COVID-19, even in clean rooms where we have to maintain certain pressure and temperature without any external air coming inside and infecting or creating any unnecessary air quality inside. So the clean rooms are going to be very specific on what quality of air you are going to get inside. So in those situations, we cannot use regular air conditioners, but we have to design it in a different way. So this depends on the customer and what they require from the building, and we have to design it in such way then we can use. Because if you take a regular CFD scenario like an air conditioner, we are just going to put a inlet patch and we will give the inlet, and it's going to create the temperature difference, is going to create the velocity, and then we will say, okay, this air conditioner is good, this is not, this flow rate is good, this is not. But in a scenario where there is carbon dioxide buildup or there is a dispersion of particles, then we cannot just approach it in a regular way, and we would need a very fine mesh and big cloud computing like HPCs in order to do this kind of simulation. And because we have a compute capability now, this is gaining traction. Otherwise, the requirement was already always there, but now we have a lot of data centers and it is becoming accessible to a lot of people. So this is gaining more traction right now. And there is industrial workspace where, as I was saying, the FDS simulation, fire dynamics, the fume extraction and thermal plumes from the machinery, and how fast do you exhaust it, and how fast can you remove a contaminant without affecting the rest of the factory. So these kind of scenarios are very necessary, but as a consultant, we would not be getting this kind of simulation because it would be done internally in factories. But if you're aiming for a HVAC role in a factory, then if you have skills like this, it's going to really help. And there are special and emerging HVAC application like displacement ventilation system. So if you remember long back, we were having window AC. Apart from split AC, there is something called the window AC, where we place the AC right on the windows and not on the top. So the way split AC works is the cold air is heavier, so it is on the bottom, and hot air is on the top. And our split AC is going to uh, cool the hot air, and the hot air comes down. The colder air becomes hotter because of our heat, the computers and the body heat, and it goes on the top. This continues as a cycle. But let's take a scenario where there is a small office inside a factory, and let's say there is a manager and he wants to get proper cooling inside his room. but it's not a confined room because it's a factory, right? So you cannot just put a split AC and expect proper cooling because it's not going to be circulating, it's just going to disperse. In those scenario, we have to place a window AC right next to his body. Then it is going to cool, and this cold air is getting hotter. It moves up, and then new cold air comes in. So this keeps happening. It is a bit tricky to design, but it is very much necessary in recent scenarios because even in small places like a foundry, people expect proper comfort at least in cafeterias, right? So we have to do this kind of simulation, and there is energy optimization. As I was saying, now with a lot of IoTs, we can control how long is your AC running, how long do you want to keep your windows open. There are IoT based windows right now. So before coming inside your home, you can turn on your AC and then you can come inside to experience maximum cooling. And with the smart HVAC control, we can take the data and we can train an ML model, and we can see how often do they turn on their AC. This is for a specific person I'm talking. So these IoT devices will get optimized in such a way that they don't have to turn it on every day. If it sees a pattern, and if it also takes the outdoor temperature, indoor air quality, and based on that, it will turn on and turn off efficiently so that you won't feel very cold suddenly and we won't feel very hot. And the manual intervention of turning on and off becomes less, and in a way, it will optimize the energy. And because of recent advancement in machine learning and big data analysis, this is becoming a huge role in the market because it's not just for individual. Let's say you are a local seller and you are selling ACs, and if everybody is going to be around the same pattern, let's say the temperature is going to change the same for a lot of people in this locality, then you can deploy a model where it turns on and off based on the requirements as well as based on general pattern. So when you buy the AC itself, it is going to have some kind of behavior where it is kind of optimized, not to a specific need, but it will be optimized. So this is the kind of advancement we are recently getting with small devices which can be attached to existing ACs as well in your switch box directly. You don't have to spend a lot on buying new ACs for that. So there are IoT devices getting manufactured now. And coming to solar chimneys and passive cooling systems, there is a buoyancy driven natural flow, right? So if you take a chimney, it is going to push out the air. But where does the air go after that? It's going to affect. If you are in a very large apartments, you cannot just put all your chimneys right to the top and then let it out. And if there is someone on the top and they also connect it to the same exhaust, it's going to get very clumsy. In such scenario, how do you passively cool it? Like, can you pass it through a lot of copper tubes, cool it passively through the external air, and then push it out so that we are not contributing to a lot of global warming? So these kind of things are gaining traction in manufacturing, but even if it is just manufacturing, we have to do the CFD in order to make it optimized. So this is slowly growing, not very much popular in India, I would say, but it is slowly gaining market. And there is radiant panels and floor heating system. As I was saying, we can place solar panels on the roof so that we can avoid heating on the roof, which will eventually heat the building. But if you place radiant panels, if you are not going to spend so much on your solar panels, if it's not within your budget, or if so many solar panels are not necessary for your building, then how do you use? Then we can use radiant panels and floor heating systems. If it is a colder area like Germany or Switzerland, then you can have a heating system instead of a cooling system. And this is like a advancement in OpenFOAM. This is by Professor Blockend. It's called Wind Driven Rain. It's an external library. You can just search for Wind Driven Rain, OpenFOAM, GitHub. You'll get a repository. You can compile it within OpenFOAM, and you can see how wind is going to affect the rain patterns. So how do you optimize your windows? Or if there is a windshield blind in a building, then how do you place it? Can you close it automatically when there is a rain? How much do you close without making the inside room hot? Because the outside is going to get very humid and eventually it gets hotter inside. Then how do you prevent it? So this kind of simulation has been done recently. And our latest kind of, I would say, simulation is solar radiation. So this is done in OpenFOAM, but I have not seen a lot of people doing it. So it's like you have windows, you have a room. If you have opaque or translucent windows, then it's going to behave differently. When you have a transparent window, it is going to behave differently. The radiation due to sun will affect your room. And there are models inside OpenFOAM where you can give the entire path of your sun with latitude, longitude of your location, and you can see how much of heat you are going to get in a specific day. So if you have those data, you can model your sun in a specific location, and you can see how much of light is going to come through your windows. It's going to serve in two scenarios. One is like how much lighting are you getting? Second, how much radiation heat are you going to get inside your room? In office setting, this is going to affect a lot because, as I was saying, when you do radiation analysis, apart from the natural lighting, you also get heating. And how do you cool it actively using your air conditioners? So now this is slowly growing field, I would say. This is done both for internal as well as external, because if you are having a huge wall which is restricting the light, or another building that is restricting light to your building, then how do you actually optimize through reflective panels to make more natural lighting into your room? So these kind of simulations are being done, and this is like a small example. You can see I have placed a block on the right side, and it is affecting how much of the radiation is passed through because it is taking in some radiation, and you can see the shadows there. And unfortunately, I was not able to put the actual numbers here because of confidentiality, but what you're looking there is temperature contour. The left is without any blockage, right is with blockage with more sun. And this is another interesting room design where we have a lot of windows we can see, and we can specifically see the patterns of how the sunlight is affecting inside the room. And if you closely look at the table, when the sun is coming through the windows, the table has a blockage which is affecting, or let's say preventing, the light from going to the other person's, let's say, computer. So how is this useful? If you have a natural lighting in a room and you have a lot of monitors, monitors are not going to like the sunlight. So how do you place your monitors, or how do you restrict the light from directly hitting your monitors or projectors? So this is something which we have done recently, and it has been successful. And finally, we have shadow casting. So this is not based on OpenFOAM, but this is also part of HVAC. I personally love this kind of simulation. This can be done in two ways. One is you can use animation software like Blender and use ray tracing within that. So there are models like Cycles, EV. EV is not good. Cycles is, I would say, is good. So you can have a light source, let's say sun, and you can give specific wattage like 700 watts or 800 watts, and you can see how much of light are you getting inside your room. So this is more like shadow casting. And can you put more shadows? Can you get more lighting? So this kind of designs can be optimized in software, even an open source software like Blender. Or if you want to go further, there is a library from NVIDIA called iRay. So you can use iRay software to do this kind of simulation, and this has been gaining more attraction in the recent times because of the ray tracing, GPU capabilities, and a lot of rendering. Because when you show it to the customers, if you show along with the shadows, it's going to be more attractive. And this can be done for even large buildings without having much of overhead, because it's ray tracing and it's done on the GPUs. So you can massively scale them on GPUs. I have personally done this only on NVIDIA GPUs. I'm not sure about other ones, but NVIDIA GPUs are really, really capable of this, especially along with Blender. If you are going to use it, use Cycles library. It will be a very interesting scenario, even if you are not totally interested in HVAC. But if you are interested in kind of rendering and animation, you can look at this, and it's going to be very interesting. And use of OpenFOAM in HVAC. So this will be my covering of how do we use OpenFOAM in Codynamics for HVAC. So mostly we are just dependent on 5 different solvers. One is buoyant simple foam. When you have heat transfer along with steady state, then we use buoyant simple foam. But if you want a transient analysis, we go for buoyant pimple foam. And if there is no heat transfer, but you just want to see the overall airflow without any heat transfer, then to make model simple, of course, there is heat transfer involved, but if you want to just model it simply, then you can use simple foam or pimple foam for steady and transient analysis. I think you will get hold of simple foam or pimple foam by the end of these workshops, because you'll get hands-on tutorials. And there is CHT multi-region foam. So this is the scenario where we have radiation, right? So we have to choose the thickness of the glass or the tent sheets. And if there is an electronic cooling and you want to put heat exchangers. So when I mean electronic, it's not like a small CPU, it's like whole data center where we have conjugate heat transfers. So CHT multi-region foam is a very good tool, and we do a lot of simulations using CHT. And combined with CHT, we also use multi-phase solvers to do like, let's say, oil dipped processor cooling in a very big HPC. Some people prefer to put it in a mineral oil so that they can cool it actively. It's not recommended, but people do it. So, how much of the cabin size do you need to actively cool the processors, the entire electronic components? So, these kind of simulation are done in CHT multi-region foam, and open foam is never short of any capability when it comes to HVAC, because even the radiation and light casting, which I showed you, was done in open foam, and without any other external tool, mostly you can do just open foam simulations, and you can get very good results. And along with some capabilities of ParaView and Blender, you can take it further to do the ray casting and shadow simulations. So this is one interesting simulation that we did. It's like what, 8 fans, and all 8 are rotating. And how do we get the patterns inside? It's not an ideal scenario where we will actually put this to use, but we just wanted to test the capability of open foam and how much can it handle, because all 8 are moving, and we are going to get a lot of velocity fluxes and pressure gradients. So this is a confined room. There is no inlet outlet, just fans rotating. And it was a great success. I wish I could show the video, but unfortunately I can't. So, and this is the 3D view of it. So we can see how good the overall simulation looks like. And another use case is actively chilled beam and actively chilled beam plus ceiling fan. So as I was saying, ceiling fans really help even if you have air conditioners. You can see how much of velocity movement you get, and which is going to affect the thermal movements as well. So we get more comfort. And this is like a planar view. Again, the same scenario. Left is actively chilled beam only, right is actively chilled beam plus a ceiling fan. And I would like to introduce you to a very small product of us. It's a work in progress. It's called the bladeless exhaust fan. And the inspiration for this product is a product called Air Multiplier from the well-known manufacturer Dyson. So we took inspiration from the Air Multiplier product, and we have made a bladeless exhaust fan, which has a lot of benefits like less noise, aesthetically pleasing, very easy to clean, and safer than an exhaust fan just exposed out there. And the current status is we hold the design patent of it. We have technology readiness level about 4. We have a prototype. We have demonstrated it, and we are in a funding phase. So we hold the design patent for it, applied for product patent, and we will be getting that soon as well, I hope. And the project scope is we have to optimize the design in the first place, because we know the product is working, the hypothesis is working, but how much can we optimize the exhaust behavior so that we can put it to actual use in a scenario where there is a household kitchen, or if there is a restaurant where aesthetics matter more than household. So instead of just a noisy, bad looking or ugly looking exhaust fan, we can place something like this, and it will be more optimally performing as well as aesthetically pleasing. That's our idea. And we are just working on the design optimization. So the overall idea here is, if you take a cross section of the circular thing which is shown here, it will look like an airfoil. And this is essentially an airfoil, but in a modified way. So you pass in air using a impeller, and this passes through the small airfoil inside of the airfoil, and there is a small slit. So this slit is going to push through the air, and because of the viscosity of air, it is going to try to stick to the wall. And when it moves out of the airfoil situation, it is going to create Coanda effect. So because of Coanda effect, on the right side you are going to get a low pressure. On the left side, which is the inside of the room, I would say, is going to have high pressure, and because of this, the air is going to move from left to right, which is the inside to out. So as you can see in this image, it is just going to move from left to right. And apart from just the inside of the circular thing that you are seeing, it is also going to take the air outside it because of the viscosity of air, and it's just going to draw in a lot of air outside. So if you are in a kitchen and if you have just a hole for exhaust fan, that's not going to be useful for this product. But if you have a window and if you just place it there, it is going to take a whole lot of air and pass it through the whole window instead of just a small slit. And based on simulations, we prove that it is much better than the regular exhaust fans in all kind of scenario. These images are not from our product due to confidentiality. This is from uh, papers and websites that demonstrate how Dyson fan actually works. And what is the design optimization scope that we are looking here? So one is there is an impeller that is working inside the product, because without any movement we cannot get airflow. So there is a duct. Inside the duct we have an impeller, and originally in the Dyson fan, it is optimized for airflow, which is the push of air bit. But we are optimizing the airflow design as well as the impeller design to provide maximum suction. So because it's a suction, it's not going to rotate the same RPM all the time. It's going to oscillate between certain RPMs, and it is kind of not an ideal scenario. So I don't want to disclose a lot here. So the impeller is there. That's the ideal scenario. And we are going to get maximum suction in the high pressure region, and it is going to push. So the overall idea is we have to create a big low pressure region so that the exhaust works properly. So what are the optimization? We have to optimize the air entrainment, how big your hole should be, like the diameter of the fan, how big should it be, and for what kind of scenario. If it's a kitchen, it could be small. If it's a restaurant, it could be big. So how much do you want to put it? And what should be the slit thickness, and what should be the lip geometry? So the slit actually matters because it is creating quanta effect, and how do you optimize to provide maximum airflow and without the flow separation, so that it sticks maximum and it provides more effect. And we also have to minimize the drag. And why do we have to minimize the drag? Because it is going to hang in just a duct, and if it is going to have a lot of air movement, eventually this hinge can become weak, which we actually experienced, and we don't want that to happen. So it has to move, and move without a drag. That is one part. But the other part, because of drag, there can be noise. So the overall idea of this fan is to reduce the noise. We are working on acoustics, but if there is going to be drag when it moves, it is going to create some noise, which we don't want. We are just going to optimize that. And it also provides like full surface guidance. It's like it should also look aesthetically pleasing. Just because we are going to optimize the airfoil, it should not look very curvy, and it should not become very hard to clean, which should not become very flumpy is what I mean. So it should be able to handle stress properly, because when you clean it, if you put load on it, it should work fine. So these are the kind of optimizations that we are looking at. And just a final note, for some simulations, we partner with a company called Tian Building Simulation. It's a German company. They have a tool called BIM, which is for Building Information Management, HVAC tool. It is an OpenFOAM based CFD tool. It has a GUI, and it can perform a lot of simulations related to HVAC and fire, and also shadow casting. And they have been in the market for a very long time, and this is how the software interface looks. And this is one of the biggest projects that they have done till now. And glad that we have been sponsored by them for some of our simulations with their software. And if you are interested in buying a software or exploring the software, you can contact me and we can look through that. And finally, yeah, this is my contact details. If you want to contact me for any suggestions related to HVAC design, or if you have any questions, like as a student, you can still ask, because as you might know, we take classes for OpenFOAM. And I mean, there are a lot of open source free resources available. And if there is something that you are not able to get through the free resources, then of course you can contact us. And if you have any questions, please ask now.
We have a question in the chat box.
What are your thoughts on skin texturing of airfoils? Actually, we tried one. There is something called the chevron corrugation. I think if this is related to what you're asking, then chevron corrugation actually helped us in the texturing of airfoil in noise reduction, basically. So it creates very local small recirculations, which helps us in preventing airflow separation as well, and also on noise reduction. So apart from that, we are not aware of any skin texturing for airfoils. Did that answer your question now? Okay. How to select an exhaust fan based on inlet fans in cooling? So inlet fans, do you mean like a ceiling fan which is placed in the room or something different? Okay. So in general HVAC simulation, there is a big problem, which is like if you even if you have any kind of electronic cooling. So if you have a cooling, let's say an air conditioner, in a regular scenario, what you might assume is every door is closed, every window is closed, you have an air conditioner and you are just passing. But the problem in HVAC CFD simulation is that because of the continuity equation, we have to conserve the mass and whatever is coming in, it has to go out. So we artificially place an outlet and it has to be moved out, even though it is not the regular setting in a building. We have to place it. But in a regular way, what happens is there will be minor leakages under your door and windows. So coming to your question, if there is an electronic cooling and there is an exhaust fan, first you have to run the simulation without an exhaust fan and see what is the maximum outflow that you are getting naturally when there is a cooling, like an air conditioner or if there is a chiller. Then because of the pressure difference, how much of exhaust are you getting naturally? Then you have to take that into account and what is the uh, whole size that you can place. So that is one thing. And if you can finalize on the diameter, then you can go for standardized exhaust fans and you can see what is the speeds available. So the thing with exhaust fans is that you cannot control the speeds unlike the ceiling fans. So you have to look at the diameter and the speed and you have to see the mass flow. So most of the manufacturers give the mass flow rate and you might know what would be your electronic cooling mass flow inlet. Then in that case, you can just choose based on the standardized exhaust fan. So first the step will be like do a simulation without exhaust fan, see what is the maximum velocity you are getting or mass flow, then see how much of exhaust do you really need the mass flow, then look for a manufacturer that gives that mass flow and then you choose the diameter of hole based on that. I hope that answers. Okay. Related to this government run hospitals, yes, CFD can help to improve the facilities, but the problem, the other problem is the scenario where they are going to place the air conditioners, like the circulation or ventilation, it has to be constructed in such way. So if there is a already constructed hospital, then it might need a bit of rework because it might not have the proper construction already done. But if you really want to optimize, then you can actually do it to certain level, maybe not totally, but it is possible if there is enough funding and there is a scenario where the building can be altered a bit, then sure, CFD can definitely help. Any other questions? Dew point evaporative cooling. So it is possible in CFD, but personally I have not worked on it. Never got the chance to work on it. But it is possible in OpenFOAM as well. So you just have to add a scalar. You don't need a multi-phase solver. You can use your regular solver, and you can add a scalar to it. And you might need a bit of modification to the solver and you can do it. But if you are looking at the evaporative cooling as such, then you can use um, phase change related solvers and it is possible. I have not worked on phase change related to HVAC directly. Sorry.
So Harish, I have something to tell you.
Yes. Yeah.
Like majority of the participants who have joined today are students, and they might be interested in applying for the FOSSEE internships and fellowships. So could you
Okay.
please kindly share your experience as an intern,
Yeah.
or give them some tips so that they can, easily clear the screening tasks and they can do a very good project in case study or research migration.
Yeah, sure. Okay. So first I'll start with my experience with FOSSEE. So I joined FOSSEE I think around 2.5 to 3 years back as a summer fellow. And when I joined, I only knew how to follow a YouTube tutorial. To be very honest, I had theoretical understanding of CFD, but I did not know a lot about OpenFOAM. But somehow I made through, and the kind of support I got at FOSSEE was very very good. And whatever I learned after that with OpenFOAM and in CFD in general, I I would give a very major portion of the credits to FOSSEE because I got really good mentors, and FOSSEE is very, very supportive. This was my experience. And the other part was I was actually an online intern. I was not able to come to the campus in person, but still I got very good support, and I got the time, even though there was a time constraint. My Professor Dheeraj Garg, and my guide was, I think, Mr. Abhushan Regmi. So they both were very helpful, and the kind of support I received throughout the fellowship actually carried forward. And that kind of inspired me to work further on OpenFOAM. And after 3 4 months, I applied back as a research assistant at FOSSEE itself, and I worked for around 5 to 6 months. In that scenario, I worked on a lot of case studies, upgrading case studies from one version of OpenFOAM to other, and I also worked on workshops like this. So the last workshop, I was on the other side. I was actually giving demonstrations. So in those setting, we actually work with other PhD people who are working in FOSSEE, the other masters and research students. So we get the kind of exposure that you will not be getting anywhere else, and you also get uh, good guidance and up to dates and updates from Pile. And it was very kind of happy and inspiring. I never thought like, oh my God, I should work today. It was very exciting, I would say. So you should definitely apply. And regarding the screening tasks, mostly the kind of task that they give is very easy. And the thing is, the screening task, you can follow any standard textbook or tutorials and you will be able to make through. But the way you put your result and the report actually matters, because a lot of tutorials are available, including my channel. Some of the screening tasks are available after they are, of course. I would say it is removed from the screen task list. I would also update it as my video. But the way you put it in the report shows the understanding that you have on the fundamental physics that is happening there. So apart from your CFD and OpenFOAM knowledge, I think FOSSEE would value the kind of understanding and approach you have towards the problem. So I would say focus on your fundamentals of fluid mechanics and heat transfer, and then you do the CFD. So even if there are minor flaws, you can come here and of course learn a lot, and it will carry forward for the rest of your life. And the kind of teaching and the support I received in FOSSEE is what inspired me to start Codynamics as a YouTube channel, and I started putting a lot of free videos out there, and it has been successful for the past 3 years, I would say. Yeah, ever since I joined FOSSEE, and I received all the support and guidance. I mean, not guidance. I was able to guide a lot of students only because of the kind of inspiration I got from FOSSEE. So I definitely recommend everyone of the participants, if you're a student, apply to it. Uh, just give you a shot, and if you are selected, then it's going to change your life. It changed mine. I hope it will change yours. Yeah.
Thanks a lot. Thanks, Harish.
Mm.
So I hope, yes, I
One
so at
more
the
question
end of the
is
workshop,
there.
yes, one more question is there. So at the end of the workshop, I'll elaborate about the internships and fellowships. I didn't talk about that in the introduction talk.
Okay.
Uh, so thanks a lot for sharing your experience. It was
Okay.
very useful because see, people actually think that it's IT Bombay thing, so it is a very tough job and all. But we are really focused on nurturing the talent or the skills that the students already have and to develop them further. And
Yes, definitely.
yeah, and that's what FOSSEE is meant for, and that's why the government of India is funding FOSSEE, so that we can raise the mediocre students of India so that they can perform well in their career. They can come up with startups. They can join the education industry or MNCs.
Yeah,
So
definitely.
yeah, yes, you can take up the question. There are I think two more new questions are
Yeah.
there.
So there is a minimum air change requirement in pharmaceutical sector. Can CFD help to reduce the air changes and save energy? Yes, it can definitely help. And the air changes, when you mean, so as I was saying in the for the previous question, regardless of whether you want or not, you have to place an outlet. So I'm not very sure about the air change, because anyways you have to push your existing air outside. But if it is just internal circulation, there is no inlet like an air conditioner, just fans, then maybe it will be helpful. But I'm not very sure about the air change. And for saving energy, yes, it will definitely help, because you can optimize the placement of your air conditioner and the amount of airflow. As you might know, the requirements of the temperature is different from what you would see in a regular household or office. So for that kind of temperature, how do you turn on and off the air conditioner with a smart setting? You can simulate the entire thing over hours and see how often can you turn on and off. This is one kind of saving energy. The other kind, the placement itself plays a major role in how long does your air circulation sustains the temperature. This is second. And the third is kind of the conjugate heat transfer kind of simulation, where you can put specific paints that are available nowadays for pharmaceutical applications, where there is a maximum insulation of the air movement. It does not go inside the concrete and cause the carbon dioxide buildup. So you can do these kind of simulation as well if you are good with chemical reactions. But in general, yes, it can massively help in saving energy. And so how can we set the heat transfer coefficient for transient and non-uniform heat transfer simulation in ANSYS flight outcome? So this is not something that I can actually answer without a proper mathematical presentation. I think when you are looking through the hands-on tutorials, I think you will get this clarified. But in general, what I would say is we cannot just set the heat transfer coefficient right out of the bat. So it depends on the geometry, it depends on the kind of simulation that you're doing, kind of material that you're using. So at least in HVAC, the material matters a lot. So heat transfer coefficient, I cannot just answer simply. Really sorry about that. So I think that's it now.
Yes, I was thinking that they don't have any more questions.
Yeah.
So even if the participants has any more question, they can directly contact you or they can contact through us.
Yeah, sure.
Yeah. So thanks a lot for the excellent session, Harish. So,
Okay. Thank you.
yeah. Okay. Please stay connected.
Yeah, sure.
Yeah. Okay. Yeah. Okay. Thanks a lot. Bye bye.